Okay, so we're to complete this, we have 2 points here. So we want to model the panda population X years after 2001. So what we're saying here is that X is going to be my year, and Y will have to be the pandas then. So what I have here is I got 2 points. I have one where I have the year is 2001, that's my X, and my Y is the 14,750 pandas. And then my other point was the year 2016, in which case I had 9,800 pandas. So if I find out the slope here, I have to pick out which ones are my Y1s and Y1, sorry, X1, Y1, X2, Y2. Like I said, it doesn't matter which points are your ones and which ones are your twos. We just have to make a decision here. So my Y2 was the 9,800 and my Y1 is the 14,750. And then my X2 is going to be the year 2016. And then I have my X1 is the year 2001. So we're changing over a 15-year period. And let me find this out again. 75 minus, and we're left with a decline of 4,950 pandas in this time, which turns into we are losing 330 pandas per year. So if we go over here and fill out this equation, so we want to write a model for this. We already decided what my X1, Y1 were, and it doesn't matter. You could use the other points as well. It'll still work out the same. But if we go based on this, my Y1 is the 4,750. I had a slope of minus 330. And then I have X minus, and what we're going to do here is going to be a little different because I want the population X years after 2001. That means 2001 is going to be my year 0. So we kind of could have avoided using this equation. So if I go through and I finish this out, we end up with this. So initially when we start at 2001, I have 14,750 panda bears, and every year I lose 330 of them. So as we were saying before, when we were comparing the Orion data, yeah, I could pick any 2 pairs of points to use as a linear model, but doesn't necessarily mean I'm picking the best way of modeling this data. So we're going to have something we call a line of best fit. So we clearly can't have multiple equations to model a relationship. It's nice to just have one. So really, we just need one because anything that I talk about when I do an analysis of the data has to be about one equation. I can't talk about several equations necessarily. It's going to get really confusing and bogged down, and we're not going to get anywhere. So we need to find one equation for the line of best that best fits the data, and this is going to be called our line of best fit. So we actually have a way of calculating this. The calculation for it is not something that I'm going to give you the equation for because it's very confusing and not very helpful. It involves a bunch of standard deviations is what it involves. So a line of best fit is a linear line that explains the relationship best. At least that's our decision. Our method of finding this line is to find one that minimizes the errors between the real data and the linear equation that we have. So what we're going to do is we're going to minimize the errors are going to occur between y, which is your real data, and your y hat. So since any linear equation is an estimate of how the data behaves, it will be prone to errors since we can't predict all the fluctuations in the data. If you remember, if you went back to the data, there was one year, I think it was year 5. We had 2 cars that were 5 years old, but they had different values to them. So we can't predict all the fluctuations. There's more going on than just age and price. There's other things that are affecting the price. We just can't control all those variables, which is what causes fluctuations in our data. So no matter what we do, we're going to have a line with errors in it. What we're trying to do is minimize them. So if we went back at that Ford Orion data, we see that a 4-year-old vehicle should cost or have a value of $10,300. This is your real data. So we're saying we have X is 4 and Y is this. However, if I use one of those linear equations, and this is the first one that I created. So if I use this linear equation here, where we said that we lost $14,000 in value and a new Orion was $16,800. If I put X is 4 in here, we get this value. So what we have here is this is going to be the real value. And this is my estimated value. And it's the difference between these that we want to minimize. So our model says, once again, the price of a 4-year-old Orion is $11,200. So what we call the error is the difference we find between the Y value of the real data and the Y value of the estimated data. Or in our case, we take the real data and we minus the estimated data. And we see we have a difference of 9 here, or minus 9 or $900. So this is my error. So what we want to do is we want to minimize the errors. And we're doing this with, this was some data that we had earlier with just a few points. So we're just going to use we're going to just use these 3 points here to talk about minimizing errors. So it's ultimately not going to matter how this goes, but as for now, when we talk about the error, it's always going to be the difference between the real data and the estimated data. And it's only referring to those Y values because we always maintain the same X values. So what we're going to do is we're going to take 2 different lines that model this data. So below we have 2 possible lines that fit, and we have the equations are right above that. So this is line A, it's modeling the same data. As you see, it happens to actually go straight through one of the points. And this is line B. So the error is the vertical distance between the line and the data point. The preferred line is the one that's going to have what we call the smallest sum of the squared errors. So what we have here is a situation like this. Kind of model it here to the side. So my first equation, I need one less bar in there. Or one more bar. So we're going to make a little chart here to the side to kind of demonstrate what's going on here. We might make a little chart if it's going to work with me. All right, so we're going to have your X and your Y that we normally have. So if you took each data point here, this one, and this one, we see we have one data point where X is 1, but Y is 3. this data point here, we have x is 2 and y is 1. And then this one over here, we have x is 3 and y is going to be 5. So what we're going to do next is we're just going to go through and we're going to figure out those squared errors. Not squared errors. I'm sorry, we're not even to the squared errors. We're going to go through and we're going to find the, there we go. Find our y hats. Sorry, my tools are like acting weird as I'm trying to do this. There we go. So my y hats, if this is the equation for line A, we're going to first look at the case where x is going to be equal to 1. So if x is equal to 1, what we get is that y is going to be -1 plus 2 times 1, which is going to be 1. If my x is going to be 2 now, then my estimated y hat is end up going to be -1 plus 2 times 2. So we're going to end up with 3 here. Then I'm going to have my x3. So I'm just using the points I had over here. And my estimate, if x is 3, what my equation is saying is that I expect that y should be 5. So next what we're going to do is we're going to do the errors over here. So if you remember, the error is the difference between y and y hat. So my first error is I have 3 minus 1, so my error is 2, which is where that comes from here. My next one is I have 1 minus 3, so I have an error of -2, which is what you see over here. And then here I had 5 minus 5, so my error is 0, which is what we see here. So when we're looking for the errors, that's what we're doing, is we're just going through and we already have x and y. We need to find the y hat for each point, and then we compare those to figure out the errors. Okay. So if we do this on the other side, very similar, do a quicker version of this. We're going to make a chart here again really quickly. So my x, sorry, caught my y's, my y hats. Well, that was weird. And then my errors. So the first part's going to stay the same. We had a point that was at 1, 3, a point that was at 2, 1, and a point that was at 3, 5. My y hats, if I was using this equation now, if x is 1, then this is telling me that y should be 2. If x is 2, then y should be 3. If x is 3, then y should be 4. So we look for those errors. It's going to be the difference between these 2 points. So 3 minus 2 is going to leave me 1. 1 minus 3 is going to leave me with a -2. And 5 minus 4 leaves me with a 1. So the next thing we need to do is we need to take those errors and then we're going to square them. So this is the last set. This is the first line that we did. So if we square those errors, they should all come out positive. And we see the sum is 8. So what we're looking for ultimately is we're looking at the sum of the squared errors. And according to this, my sum of the squared errors is 8. So we're going to look at the sum of the squared errors for line B as well. So if you look at line B, we had an error of 1, -2, 1. So we get errors of 1, 4, and 1. If we add those up, we end up with 6. So the sum of squared errors for this line is going to be 6. So what we have here is that since line B has a smaller sum of the squared errors, we are going to say that it is a better fit than line A is. Not necessarily the best fit, but we know it's a better fit. So ultimately, how we decide on our best line is what we're going to do is the line of best fit leads us into what we call the least squares criterion. Sorry. Got a little off there. So the least squares criterion is that the line that best fits the data is the one that has the smallest possible sum of squared errors. So like I said, out of the last two lines, B had a smaller, line B had a smaller sum of squared errors. It was a better line of fit. Wasn't the best line of fit necessarily. A line that befits the data, the line that best fits the data points according to the least squares criterion is called our regression line. So if it satisfies that least squares criterion that we mentioned up here, that is what we're going to call a regression line. And of course, the equation for your regression line is going to be called your regression equation. So like I said, least squares criterion is the line of best fit, has the smallest possible sum errors. That line that has the smallest possible sum errors is called your regression line. The equation for the linear regression equation uses standard deviations of your x variables, your y variables. So it's the distance between changes in x's, changes in y's, and then like this combination of the two. So like a not horizontal, what I'm thinking. It's a difference between your x, y as together to another x, y. So it's like comparing the points sort of diagonally. This is very laborious calculation. It's not going to help you understand how to do this any better. The least squares criterion tells us what we're looking for, so we're not going to really focus on necessarily how we do this calculation. You'd be here all day just trying to do through points with it. So what we're going to do is we're going to use some technology that we have. So we have a calculator that helps us find the linear regression line and equation. So if you remember that Orion data, that's what we have over here. So I'll show you this calculator in a bit. But this is using the Alkila calculator. So you should have this one linked. And this is one of your statistics calculators. But this is going to be your linear regression calculator. So the linear regression calculator is also going to give you a scatter plot and a line through the data. But according to this, if I do my least squares regression criteria and we try to find a line, this calculator says that my regression line, sorry, that was supposed to be a highlighter, says that my regression line is this line right here. Or another way of writing it is saying we have y, and I'm going to like round this. So this first point is 195 point, we're going to round that to 2 decimal places, 47 minus 2000, 20.26, and we see the x's here. So that's how I end up with this line here. So if we enter the Ford Orion data into the calculator, we see that the regression line of the data is approximately a negative 20.26x plus 195.47. So So according to best line of fit, the price of a new Orion is actually $19,547. And we're actually losing $2,006 in value every year. So that is what your regression equation does. And in this case, previously we had done this and we said that according to the data, if a car was 4 years old, then its value was supposed to be 103, or as we said, it's 10,300. If we put 4 in this equation, like we do down here, we're getting this value instead. So one of the things to notice is actually this regression equation is closer to that second one we did when we used the endpoints. The endpoints wasn't a bad way to calculate this regression line, but as I said, if we run it through the regression calculator, which goes through all the calculations that finds this line, it's going to actually be this line right here. That is your linear regression line. So if you're going to do this murder rates and poverty, oops, didn't do what I wanted it to. If you use this data here, so the data to the right is the regional data from the 1970s on the percentage of homes with incomes below $5,000 a year. So remember this back in the 70s, and the number of murders per 1 million people in that year in that same region. So if you want to make a scatter plots data and find the linear regression, correlation, coefficient, and regression equation, what you need to do is you need to go to your calculus statistics calculator, and we're going to do linear regression. So just type in that data. So the first data point is the 16.5 was your X, and then the Y was the 11.2. So just keep putting all that data in, and then when you hit submit, that's what's going to give you your scatter plot and everything. So I'll give you a chance to work on that and answer that question in your homework. So if you need that linear correlation coefficient, once you put that data in, as we saw last time at the bottom, you'll see a spot where you can just hit and gives you linear correlation coefficient. So it's the same calculator as we were using last time. But after you do that, then just go through these questions. What's the relationship between poverty and murder rates? What is the strength of the linear relationship? And then what percentage change in murder rates is predicted by change in the percentage of families in poverty? So what we're looking at is linear correlation coefficient questions. So just kind of a review of that. So the first one is it a positive relationship, a negative relationship? Does it look like it's strong? And then the last part, we're talking about that percentage that is looking for that coefficient of determination.